Okay, so welcome everyone to this new SIPTA seminar. So today we are very happy to receive Marnix Suilen. I hope my pronunciation is good, but or not too bad at least. And he will talk to us about sequential robust decision process. So today we receive Marnix. So Marnix is currently postdoctoral researcher at the University of Antwerp or Antwerpen. And before that, it is his PhD in Nijmegen. And Marnix is therefore a young researcher, but he has already quite a number of impressive results, and many of them are about sequential decision models and particularly Markov decision process, and I will talk about them in these talks. So when I say he has already a lot of impressive results, is that you can check his webpage, and he has done, I think, all the major or most of the major AI conferences that one can think of. This includes AAAI, HCI, NeurIPS, if I'm correct, and also Concur, which is more a conference about distributed computing. But so Marnix has a wide knowledge of such in decision process and in sequential decision process, and in particular, he has dealt with them with imprecise probabilities, without, I think, meeting much of the SIPTA crowd so far. But this is a very good opportunity to invite him and to get to know the crowd and for us to know a bit more about Marnix's work. So Marnix, we are very happy to have you here for this virtual seminar. And without further ado, I will give you the floor. Yes.
Okay. Yeah, so thank you for having me. Indeed, I've worked with, let's say, imprecise probabilities or sets of probability distributions in my work quite a lot, and but mostly from the formal methods and AI perspectives, and not really interacting with your community until today. So it's very nice to be here. Yeah, so hopefully at the end we can have some nice questions, some nice discussion on how these works interact and relate, that kind of stuff. So as mentioned in the introduction already, I'm a postdoctoral researcher at the University of Antwerp now, and I will talk to you about robust, partially observable Markov decision processes. So this is a very general model for sequential decision making that captures lots of scenarios, and this is a particular stream of work I've been dealing with since the start of my PhD. Yeah, so without further ado, let's go into this. So I will first give a general introduction into decision making under uncertainty and the basic models we'll be using, and then we'll move on to these robust, partially observable Markov decision processes, which are, as I said, kind of a very general model that tries to deal with several aspects of uncertainty at once, and that makes their semantics quite complicated. So that's what the second part will be about. And then at the end, we'll look at some algorithms, a bit more of a practical perspective of how to deal with these types of problems. So decision making under uncertainty. This is a very general area which has many applications, right? So in healthcare, finance, ecology, robotics, and kind of the classical example we typically use for these types of models that I will be talking about is a robot navigation problem, right? So as illustrated, we have some kind of robot that has to navigate a grid world, and it wants to reach a certain goal without running into any obstacles. Maybe there's an adversary moving around. Maybe the robot has imprecise movements, right? So that's where probabilities and uncertainty come from in these types of scenarios. And this is the slide I was talking about, right? So we have as I said, this typical grid world example of a robot that wants to navigate around, and maybe there are some obstacles. And there's typical forms of uncertainty from imprecise actuators, right? So the robot may not move precisely. There's an adversary that moves around That's where uncertainty comes from. So the standard model to capture these types of decision-making problems are Markov decision processes. And a Markov decision process is a finite state model. So we have a finite set of states, a finite set of actions, a probabilistic transition function, a reward function that assigns a value to certain actions, and then a discount factor, which is typically just used to deal with infinite horizon problems. And the way that such a model evolves is quite simple, right? We are in a certain state, and then our agent can select a certain action, so go left, and then with some probability distribution, you move to a successor state. Policies in these models select actions, and in general, they are path or history based. So they consider all the past interactions, and based on that, you select an action. And typical objectives are to find a policy that maximizes some measure. And the classic example is the expected discounted reward, which is depicted in this equation here. So it's discounted because we have this discount factor. That's a value smaller than 1, and that ensures that this infinite sum is a contraction, so it converges. So discounting basically takes care of some mathematical problems. There are other objectives we can also consider in these types of models. Finite horizon rewards, maximizing a reachability probability, stochastic shortest path, all these types of problems. And for most of these objectives in Markov decision processes, memoryless deterministic policies, so policies that just select a single action for each state, are sufficient, which includes discounted reward. And if we have an MDP and a policy, then we can compute its value, so the reward we obtain through the associated Markov chain. So I can take my policy, put it on the model, and then I get a Markov chain, which is hopefully a model that several of you have heard of before. And this is uniquely defined, and it gives us a probability measure, right? All the good stuff that you want is there, so it's all well defined, and this value exists, all that kind of stuff, right? So this allows us to actually compute things. And then we have algorithms like value iteration, policy iteration, or linear programming that can solve Markov decision processes. And in particular, these are all based on the Bellman equation, which is depicted here, right? So this is the recursive computation to maximize the discounted reward in this case. And this equation has a least fixed point, which is then the optimal value. So that's in a nutshell solving Markov decision processes. Now we're going to make things a bit more complicated. So Markov decision processes are fully observable, right? So the state is always precisely known to the agent, and this is an unrealistic assumption in practice, right? So many real-world problems have incomplete state information, which in our robot example may be, for example, due to imprecise sensors, right? So the robot has to sense its environment to detect whether there's an obstacle or not. And these sensors may also be imprecise, and this gives us certain observations. And that hides the true state from the agent. And so partially observable Markov decision processes, or POMDPs for short, are the natural extension of these types of models. So we just take our MDP that I just introduced, and on top of that, we are adding now a finite set of observations and an observation function. And the nice way to depict these models is to just color the states, and the agent cannot distinguish between states of the same color, right? So that means that if we are in a red state, then we have to take the same action there. regardless of whether we're in the state on the left or on the bottom. And there's a simplifying assumption that we can make that allows us to make deterministic state-based observations instead of randomized ones. This can be done by encoding these observations in the state space. That's a technical detail, but it's nice to have for computational reasons. So how do you then solve a POMDP? Well, in principle, a partially observable MDP is equivalent to a fully observable MDP by just expanding all the possible histories. So a history is just a sequence of the observations and actions we've seen so far. And if we are in a certain history H, then, and we take action A and then see some observation Z, then we get a new history by just appending these things together. And so this fully observable history MDP is essentially an infinitely growing tree. We can compress this model a bit. You can compress it into distributions over states that are called beliefs, and this gives you a slightly nicer model to work with, but in general, all these models will still be infinite state. And for that reason, most objectives in POMDPs are also undecidable. So optimizing or finding the optimum is not generally possible. And policies, they need to be history-based and they need thus memory, right? So we really need to remember past interactions to make optimal decisions. And in general, you could need infinite memory. So you may have to remember everything that happened before. Finite memory policies, where you only look at the last k interactions, typically can yield good approximations. And these finite memory policies, they are also nice because we can represent them by an automaton called a finite state controller, which is depicted on the right here. So what's a finite state controller? It's basically a set of memory nodes. And if the agent is in a certain memory node, upon receiving an observation, for example, Z1, an action is selected with some probability distribution. This action is then executed in the environment. And after that, with some probability distribution, the successor memory node is selected. And if you have such an automaton that represents your policy and you have your POMDP, you can take a product construction, and this will again give you a Markov chain that again uniquely defines the value. And so we can efficiently evaluate the performance of such finite memory policies. So that's a very nice thing to do. And so if you want to solve POMDPs, then there are several algorithms. It's kind of an entire area of research on its own to make this problem tractable and to make it efficiently solvable. So the classic work is basically taking value iteration and being clever with how you deal with these beliefs that I just mentioned. So it gives you point-based value iteration, heuristic search value iteration, these types of algorithms. You can also approximate the value through Monte Carlo tree search. It gives you an algorithm called POMCP. And you can use these finite state controllers I just introduced to do policy iteration kind of procedures. So you take some initial finite state controller and then you try to improve it over and over again until you get stuck. So these are typical ways to solve these standard POMDPs. But that's not really why we're here today, because I want to talk to you about robust partially observable Markov decision processes. So what are those? Well, the models I just introduced, MDPs and POMDPs, they assume that the probabilities are precisely known. And hopefully, as several or most of you within this community will agree with me, is that having exact probabilities can be an unrealistic assumption. So in these models, it's known that the optimal policies and values are highly sensitive to small perturbations in probabilities. So if I take one model and I just change one of the probabilities with just a plus epsilon and some other one with minus epsilon, the value can be completely off. And also, the policy that I compute can select different actions. The second argument is that probabilities are often estimated from historical data. This is done in applications such as statistical model checking or reinforcement learning. And when you start to estimate probabilities from data, you naturally will introduce some kind of statistical error that you want to account for, right? You cannot just take a point estimate and then assume that will work well because of the first point I just mentioned, right? So if you're off by a little bit, this can have massive influence on the results. And the third point is that these finite state models, when you use them in practice, are almost always a form of abstraction, right? We have a complicated real-world problem, for example, our robot navigating a grid, and we just compress or abstract this into this finite grid with cells and maybe some adversary moving around. This is naturally an abstraction, and this abstraction will always be wrong in a sense. So it's just a question of how can we make a model that is useful in practice. And to that end, people have introduced robust Markov decision processes. So what is that? Well, it's an extension of the standard MDP I showed you before, but now with, well, let's say imprecise probabilities. Or to be a bit more precise, there is an uncertainty set, which contains sets of probability distributions, and the robust MDP defines then a set of possible MDPs. Right, so I have a transition function, a standard transition function with exact probabilities for each element in my uncertainty set. And kind of the most intuitive example of such a robust MDP would be an interval Markov decision process where each transition is assigned a probability interval, as in this example. But you can allow for more general types of uncertainty sets. So intervals are just kind of the basic example. And semantically, these robust MDPs, they form a stochastic game. So we have our agent, which selects actions, and we now have an adversary which selects transition functions from this uncertainty set. And the agent wants to maximize the reward, the adversary tries to minimize, and this gives you this sub-inf or min-max type of game, right? And I have this notion of an optimal value and policy still. But we need assumptions for this to work, and this is where it can get a bit tricky. So we need to make assumptions on this uncertainty set. And the most common one is that the uncertainty set is what's called SA rectangular. And that essentially means that it is independent for each state action pair. And I will have an example of this later on. But it essentially means that I have a set of smaller uncertainty sets, one for each state action pair, and then the global uncertainty set is just the product of that. You can allow for something similar on just the state level. So you allow for dependencies between different actions, but not across states. And then we also need to assume that these uncertainty sets are typically convex. For example, polytopes, because that's nice for computational reasons. There's another semantic aspect we need to consider, which is the static versus dynamic uncertainty. And this has to do with how our adversary behaves. So in the static uncertainty model, the adversary chooses one transition function right from the start from the uncertainty set and sticks to that. So this is really a setting where you have a set of models. One of these models is selected, and then you as agent try to optimize for this one unknown model. In the dynamic setting, the adversary is really allowed to choose at each step. So that's really the game setting where you play one turn after another. And a very nice result from the robust MDP literature is that as long as both players play memoryless, so they just select based on the current state, it is actually, it doesn't really matter. Static and dynamic uncertainty coincide. They will produce the same value. And this is a very nice result because that allows us to just pick whichever one of these two is the most convenient and work with that. Okay, so to look at a small example, so a robust MDP can just be considered as a standard MDP where we have a bunch of variables and our uncertainty set tells us which values these variables can take, right? So in the SA rectangular setting, I just have a unique variable at every transition and they don't influence each other, right? So at state S0, action A1, I just have X1 and X2. And at action A2, for example, I have different variables, right? So there's no overlap there. So they are completely independent. And this is nice to work with. In the S rectangular setting, I have this variable y, which occurs at both action A1 and A2 for state 0. So there's a dependency here, right? So if the adversary chooses, let's say, 0.1 for y, then this 0.1 will also occur on the second action. And then there's the third most general case, which is non-rectangularity, where the dependency y now occurs across different states. So then you have a really complicated model with intricate dependencies. And there is also a kind of ordering to these rectangularity assumptions, because basically you can think of SA rectangularity as being the most conservative because we give our adversary the most power, right? Is as soon as we start to introduce these dependencies, then the adversary will be restricted in what it can choose. And why is this SA rectangularity in particular nice to have? Well, if you look at the standard Bellman equation for MDPs, which is given here above, you can simply extend this to account for the worst case, right? Because we are only dealing with uncertainty at a state action level, we can introduce this worst case selection in the middle of our equation here through this infimum. And this gives us a local optimization problem. And that means that this robust Bellman equation is still nice. It is a contraction mapping. It has a unique least fixed point. All the good stuff that we had before still holds. And thus, value iteration, policy iteration, those types of algorithms can be extended easily. So this is why SA rectangular robust MDPs are nice to work with, especially if the uncertainty set is convex, like I mentioned before, for example, a polytope, because then this inner infimum you see here is actually just a linear program. So you can solve this efficiently. So that's fully observable robust MDPs. In a nutshell, there's way more to talk about, but I'm trying to just give you the basics that we need to go to the real meat of this talk, robust, partially observable MDPs. And there's an interesting thing going on there already. So there is some initial work that gave a definition and algorithms based on value iteration from 2015. And then at the start of my PhD, my co-authors and I worked on some convex optimization approaches in the early 2020s. And then only more recently, we actually started looking into the semantics of these models. So the interesting thing is that there's a bunch of algorithms around, but nobody really formulated precisely what problem they were solving. And well, as you can see, this leads to some interesting results. So I will now first discuss the semantics, and then afterwards we'll get into some of these algorithms a bit. And so this is based on the paper Imprecise Probabilities Meet Partial Observability, Game Semantics for Robust POMDPs. And this was published in HKIND 24. So the intuition that we're trying to work with here is that a robust POMDP should just be a robust MDP, as I just introduced, with partial observability, right? That's the basic idea that you would hope to be working with. And so if you want to formulate this in a tuple, you can, right? So you still have your states, actions, the uncertainty set, reward, and then you add the observations from a partially observable MDP. And in general, we define observation functions for both players, right? So for the agent and for the adversary. And to define the semantics, we'll now be looking at finite horizon rewards instead of discounted infinite horizon. The nice thing about finite horizon is that things are at least decidable in the general, in POMDP setting. And that helps a bit with figuring some of the semantics out. And basically, the first result that we came across when looking into this was that these notions of static and dynamic uncertainty from robust MDPs no longer coincide. And instead, we introduced this notion of what we called stickiness, because we need some kind of range now. And the intuition there is that, so you have these variables, you want to assign numbers to these, right, valuations. And some of these valuations may stick, so they remain fixed over time, and others are reset. And so that's why we called it stickiness. And we have two extremes here that coincide with the static and dynamic uncertainty semantics from before. So zero stickiness is just dynamic, right? So nothing ever sticks and it's always reset at each step. And full stickiness is everything sticks from the start. And then you can also define some kind of partial stickiness, right? Some in-betweens, because zero and full are really the extremes. And the dynamic model, right? So the zero stickiness model provides a conservative lower bound, because again, this is about giving your adversary the most power possible, right? So that will always give you the conservative lower bound. And we can show that for the finite horizon reward problem, we can construct two robust POMDPs that only differ in their stickiness functions, and and then they have different optimal values, right? So it really matters what choice you make here. Everything else is the same, the state, the uncertainty set, that's all the same, yet you just change these two semantics and you get different values. So it matters what you're doing here. And it kind of makes sense, right? Because the theorem for robust MDPs that said that static and dynamic uncertainty coincide, that one explicitly assumed both players are memoryless. And that's not the case in general in a POMDP. You really need memory, and that's where this goes wrong. A similar result can also then be obtained if you change the order of play. So that's just which player moves first, whether it's the adversary or the agent. And that also matters. To then formally define the semantics of these robust POMDPs, we show that these models are equivalent to a two-sided partially observable stochastic game. So this is really expanding the intuition, right? So we have two players, there's partial observability, and they play against each other. There is a technical problem here a bit. Two-sided partially observable stochastic games are relatively understudied, I would say. There's not much work on that. Most of these models assume one-sided partial observability, not two-sided. And our adversary selects probability distributions from a set. And this set is uncountable in general. So that would give an uncountable set of actions for the adversary, which is also not something that these models typically deal with. And that's really where the technicalities of our paper come in to then still show that this defines a proper game, and we have bijections between the paths, histories, and policies of the robust POMDP and the game that we define, and thus we can also show that the values then coincide. So this is really the semantic model of a robust POMDP. And as a byproduct of that, we can then also get that these games satisfy a saddle point. So that basically means that the sub-inf equals the inf sub. And from that, it follows that a Nash equilibrium exists, which again helps with defining or with saying that these values that we are interested in are well defined and can actually be computed. So that's on a very high level summarizing the technical semantics we have. So it's really about properly defining the stochastic game that underlies these models. And as I mentioned before, the timeline is a bit weird, right? Because we had all these papers with certain algorithms, but then what are they solving? So we also classified those previous works. And there is a kind of a clear split between works. So either papers assume the zero stickiness or dynamic uncertainty model where the agent moves first, or you assume the static model where nature moves first, right? And this kind of goes hand in hand because the static model is really the setting where the adversary selects a model and you just don't know which one you're playing in, but it remains fixed over time. So it's a natural setting, and the dynamic model is way more the game-like fashion. And this also reflects in the type of algorithms that these papers define, right? So the zero stickiness or the dynamic papers, they are all value iteration based. And as we've seen in the robust Bellman equation, right, it also kind of defines this game-like notion where the agent selects an action and then the adversary selects a probability distribution. Whereas the two latter papers, they are convex optimization based. So they really formulate one big optimization problem and then solve that. And on that, I will also get into a bit more detail. With the last part of this talk, let's look at some algorithms. So I will talk about two particular algorithms in detail. So the convex optimization approach I just mentioned, and then an alternative using recurrent neural networks. And the convex optimization method computes finite state controllers. And to do so, we need a finite state controller, as I've just shown before. And for that, we need to fix a memory structure and then encode it in the state space. So what does fixing a memory structure mean? It's essentially assuming a graph for our automaton. We don't need to assume the probabilities just yet. That's what our algorithm will do. So it will fit probabilities on this graph, essentially. And to do so, you can formulate this problem as as a non-convex semi-infinite optimization problem. So what does that mean? Well, we have constraints of the form shown here below, and it's non-convex because we are multiplying variables with each other. So we have variables v and pi, so v for the values and pi for the policy, and these are multiplied, so that's a quadratic constraint, and these are non-convex in general. And it's semi-infinite because we have this universal quantification over our uncertainty set, right? So if we assume SA rectangularity, that helps a bit, but still we are quantifying over an uncountable set. So we have, in principle, an infinite number of constraints. So this is a problem that, sure, you can formulate it, but on its own, you cannot do much with it, right? So we need to do some work. And to do so, we kind of do an iterative procedure. You could think of a bit of a policy iteration type of procedure where we deal with the non-convex part and we also deal with the semi-infinite part. So there is a technical step which allows us to split concerns. And so instead of the general constraint I just showed you, you can split those constraints into two separate constraints. One that only has the non-convex part, so the multiplying of variables, and one constraint that only has the uncertainty, so the universal quantification. And what you can do then is, for the universal quantification, you can use standard methods from robust optimization to dualize this problem. And for the non-convex part, you can then use linearization methods to transform it into a linear program. Linear programming is nice, you can solve it efficiently, but this is an approximation, right? So this is an approximation around a initial finite state controller. So you solve this, you get a value and a new finite state controller, and you can then improve this again and again and again. So you linearize around previous solutions until convergence or a timeout or maximum number of iterations, those types of criteria. This algorithm is guaranteed to converge, but only to a local optimum. And that's natural because already in standard POMDPs, optimizing infinite horizon problems is undecidable, right? So we should not be able to find a global optimum, not efficiently at least. And the found policy and value is a sound lower bound to the optimal or near optimal policy or value, right? So it's a conservative bound. So the value that you get out of it is a hard guarantee, right? You can really use this in practice. The second approach using the neural network is kind of similar in spirit. So before we had these finite state controllers, and as I said, they are nice, right? They're automata. We can efficiently and exactly evaluate the value of a policy, but the downside is we need to predefine this structure, right? We need to assume this graph. So how do we find a good memory structure? It's kind of an open problem here. So you could, well, also iterate over all kinds of graphs, but that seems like a bad idea. Instead, what you can do is use a recurrent neural network, which is essentially an infinite state machine. And that one can actually learn memory structures from data. But the downside is that policy evaluation is not exact, right? Because we have this infinite state machine, so a product construction isn't going to help us. And instead, we have to rely on simulations, which are not great. So we want to somehow combine these two worlds. And to that end, we have the following framework. So the idea is to iterate over POMDPs within our uncertainty set. Right? So you start with some initial POMDP, some initial transition function. You find a finite state controller that works well for that one. You evaluate that finite state controller, right, which gives you a robust value. And based on that robust value with a linear program, we can select a new POMDP that is a local worst case instance to the previous solution. So in a sense, we're again iterating over finite state controllers with locality guarantees. And in a bit more details, how does that work with the recurrent neural network? Well, a recurrent neural network can just be trained on data. So you put in the histories, sequences of observations and actions, and then you can basically use a technique called a quantized bottleneck network that will transform this recurrent neural network into a finite state controller. So you extract a finite representation. And from that, you can then do the loop I just described. Right, and these finite state controllers can be evaluated exactly, which can then help us to construct this local linear program to find good instances. So in spirit, pretty similar algorithms. It's more about how do you iterate over the finite state controllers. That's the difference. So we have some experimental evaluation. So we compare the neural networks with the convex optimization approach, which is called SCP in these graphs here. And we also have a baseline which does the RNN structure, but then only on fixed POMDP, so without the pessimistic POMDP selection. Right, so you can, instead of iterating over different POMDPs, you can also say, well, what if I just randomly select one POMDP from my uncertainty set and compute a policy on that? And who knows, maybe I get lucky and maybe it will work well in practice. So that's kind of the experiment that we did here. And in this particular case, we focused on the stochastic shortest path objective. So that's a minimization problem instead of a maximization. But yeah, both algorithms extend also to discounted reward maximization, reachability, all these types of objectives, they all work in a similar way. Yeah, so we'll be looking at the worst case performance. And since we are minimizing in this particular instance, lower is better, right? So, and what we see here is a couple of interesting things. So in general, the neural network manages to find better policies than the convex optimization method, except for on one model. So on this intercept model, the convex optimization method manages to find a better instance. And the convex optimization method, as mentioned before, you need to fix a memory structure, right? So that's what this K represents. That's how many memory nodes are in the finite state controller. And there's also an interesting thing going on there, which in theory, more memory is always better for POMDPs. Yet, for this convex optimization method, if we add more memory, right? So if you look at the k equals 9 row, you can see that most of these actually perform worse than the k equals 3 method. And the reason is that you get stuck in a different local optimum, and this is just a worse local optimum than the other one. So the intuition that more memory helps is also not always true in this setting. Then the comparison with the RNN baseline. So basically what happens is you see a lot more variance already in the different baselines, right? So it really depends on what you pick and how the network is trained, whereas the iterative scheme that we used in our method, right? So RFSCNet is more stable, and generally produces lower values. Which essentially says that it's worthwhile to account for this type of uncertainty in these sequential decision-making problems. So that brings me to conclude this talk. So what I would like you to take away from this talk primarily is that robust POMDPs are a very nice model. It's very interesting, lots of open problems also, but it's not just a case of taking the robust MDP, slapping some observations on it, and we can work with that, right? So all these types of assumptions that don't really matter in the fully observable case do matter here. And approximation techniques used in algorithms may actually further muddy these semantics. Because I did a bit of a weird thing here. I told you about the semantics, right? And this stickiness and how that influences values. And then I presented algorithms without telling you what semantics we really assume. So the algorithms I just presented in principle assume the static setting, right? So full stickiness. But then we start to use approximation techniques in these algorithms, right? So we start to iteratively solve this convex optimization problem, to iteratively train and update our neural network. And that's a bit more of a dynamic setting. Nonetheless, our results are sound because we have this exact policy evaluation using finite state controllers. And that one is on a robust Markov chain. And if we assume the dynamic or zero stickiness model there, that is, as I mentioned before, a conservative lower bound for everything else, right? So in the policy evaluation step, when we compute the actual values, we just give the adversary all the power it could possibly have, and that way you at least get a sound lower bound. But if you have a specific problem where you can actually limit the power of your adversary, then this lower bound is very conservative, right? And so that's also a real direction for future work, right? So how can we create exact, less conservative algorithms? Yeah, and then there's also some other open questions, right? So the game semantics I introduced, they are only for finite horizon rewards. Most of the results we believe will extend to, for example, discounted infinite horizon, but there could be some technicalities there where we're not entirely sure about yet. And then there's also some computational complexity questions, right? So some problems in POMDPs are decidable. For example, the finite horizon reward. Does that belong to the same complexity class, or does introducing this uncertainty make the problem harder? That's also an open question. And that's it. So here's a short list of references. So I think I tried to cover a lot of ground. So hopefully you found this interesting and informative. Some standard references for POMDPs and robust MDPs. So for POMDPs, we have Kelbling et al. And for robust MDPs, I usually really like the Robust Dynamic Programming paper by Ian Gar. We also had a more recent survey article that kind of summarizes a lot of results on robust MDPs. And then for the robust POMDPs, these are the three papers I talked about, right? So the semantics and then the two algorithms. And yeah, so that's it. And hopefully you found this interesting, and I'm happy to answer your questions.